So far in this course, we've covered the basics of cloud computing in AWS, including computing in EC2, Lambda, and Beanstalk. If you recall, EC2 were AWS's virtual machines that are highly configurable. Lambda is compute power that's completely managed so that you don't have to mess with the operating system or the underlying instances. And Elastic Beanstalk was a very easy way to get applications up into the cloud very quickly. We also covered S3, EFS, and Glacier. We pointed out that S3 was very easy to use and intuitive object storage. Elastic File System was highly scalable and shareable storage for EC2 instances and other occasions. And Glacier was very affordable, infrequent access storage. We also very quickly covered the difference between regions and availability zones, and we pointed out that regions were different physically isolated places that AWS offers you to deploy resources into, and that each region had multiple availability zones inside it. Another thing we covered was the shared responsibility model, and we talked a little bit about which parts of your security are your responsibility and which parts are AWS's responsibility. And finally, we touched on AWS service limits and how to get around them by completing a service request. For EC2 instances, we learned what an EC2 instance is, which is the fundamental virtual machine that AWS offers for compute in the cloud. We learned that from the EC2 dashboard, you can view running instances, and then for each instance, you can view all sorts of information, including any public DNS information it has, the VPCs and subnets that it's attached to, any security groups that it belongs to, and IAM roles that it belongs to. We also learned that if we launch an instance, we get to decide the AMI, or Amazon Machine Image, that we use for it. We also get to decide which instance type we use for it, which pertains to the amount of CPU and memory it has, how to deploy it into different subnets or VPCs, and then how to assign different IAM roles to it, what EBS is, and how to both change the amount of storage that's stored on EBS, as well as attach multiple EBS volumes to it, how to configure security groups, and then finally, how to use key pairs to access the server once we've deployed it. We learned that security groups control ingoing and outgoing access for servers. And we also learned how to use launch configurations and auto-scaling groups in combination with load balancers and target groups to automatically scale in and out for our EC2 instances. For S3, we learned what S3 is, which is Amazon's fundamental, very intuitive bucket and object-based storage service. We learned that storing something is as simple as having a bucket and a key, which is location inside the bucket of any object. We learned that when we upload a new object, we can choose storage classes, encryption, and we can also add metadata and tags. For buckets, we learned that if we create a bucket, we can enter specific unique DNS compliant names and choose a region that we deploy the bucket into. We also learned that we can enable versioning and server access logging for the bucket, as well as encryption using a couple of different methods. We learned that while creating a bucket, we can also edit permissions for different owners and users for that bucket. Also, for any particular bucket, we learned that we can change its properties, including versioning, server access logging, default encryption, and several others. And finally, we learned that we can change the bucket policy to allow different people to perform different actions on the bucket, and then we can also edit our cross-origin resource sharing using CORS configuration for the bucket. For CloudFormation, we learned what CloudFormation provides in the form of automated infrastructure as code. We learned to look at CloudFormation templates and see the individual pieces for what they are, including parameters, which are ways to input different parameters into a CloudFormation template, mappings, which are ways to map different values to different keys based on input, and of course resources, which represent actual resources and functions that you're going to create as a result of this CloudFormation code. We also learned that for any CloudFormation stack, we can provide outputs for other stacks or for our own reference. We learned about using CloudFormation intrinsic functions to grab different pieces of metadata and to perform other functions that we might need inside a template. We also learned about CloudFormation transforms, which we can use for a variety of different resources, including AWS serverless. We also learned that we can integrate CloudFormation with another AWS service called Systems Manager, and in particular a service called Parameter Store, to securely grab parameters for use in a CloudFormation stack. We learned that a CloudFormation stack is a CloudFormation template that's been turned into actual infrastructure. We also learned that a stack set is a stack that's been deployed to other accounts from the account you're in. For DynamoDB, we learned that it's a fully managed NoSQL database service that provides very fast and predictable performance with seamless scalability. We learned that with DynamoDB, we can create database tables that can store and retrieve any amount of data and serve any level of request traffic. We also learned that we can scale up or scale down our tables' throughput capacity without downtime or performance degradation, and we can use the management console to monitor our table's resource utilization and performance metrics. We learned how to create DynamoDB tables and then how to configure them. We also learned how to insert items into tables, as well as view different metrics for our tables, set different alarms for our tables, and then view and configure several other settings, including our global secondary indexes. We learned about throughput capacity for both reads and writes and how that pertains to DynamoDB's pricing. We also learned how to calculate throughput capacity for different situations, as well as the difference between strongly and eventually consistent reads. We also learned about partition keys and sort keys and how to use them in our tables. And we learned how to keep our DynamoDB data encrypted at rest, as well as some best practices that we should adhere to when managing DynamoDB. For VPC, or Virtual Private Cloud, we learned what a virtual private cloud is, which is an AWS-provided networking tool that you can use to protect and segregate your different resources. We learned that on the VPC dashboard, we can see a list of all different resources pertaining to VPCs in all different regions. For example, right now I see that I have 2 VPCs in the US East region and 1 in every other region. Similarly, I can see the amount of subnets in each region. We learned that subnets were ways to segregate resources within your VPC, and that you can deploy subnets to different availability zones inside your region. We learned that deploying resources into multiple availability zones is a great way to stay highly available and fault tolerant. We learned that route tables were ways to associate different subnets and the resources inside those subnets with different routes. And that if a route table has a route for an internet gateway, that means that any subnet associated with that route table is a public subnet. Similarly, we learned that if a subnet isn't associated with a route table that has an internet gateway, it's not a public subnet, it's a private subnet. We also learned that if a subnet isn't explicitly associated with any route table in a VPC, then it's implicitly associated with the main route table. And finally, we learned how to control security with both network ACLs and security groups, and that the difference between the two is primarily that network ACLs control security at the subnet level, and security groups control security at the instance level. For IAM, or Identity and Access Management, we learned how to add users by going to the Users dashboard and clicking Add User and giving them a name. We also learned that we can give users either programmatic access or AWS Management Console access, or both if we prefer. We learned that we can give them an auto-generated or custom password. We also learned that we can give them permissions using a few different methods, either by attaching existing policies directly to them, copying permissions from an existing user, or the way that AWS recommends, adding them to a group. We learned that once a user is created, we're able to manage their security credentials for them, as well as assign multi-factor authentication devices if we prefer. We also learned how to create and rotate access keys for their programmatic access. We learned that groups are a great way to give users permissions based on their job role. We learned that once a group is created, all we have to do is select it, and then add users to the group, or remove them from the group if we need to. We learned that the way we attach permissions to groups are through policies, and that AWS provides many different AWS managed policies that we can choose from. Managed policies are groups of different permissions with different scopes, so that we can choose many different permission groups based on our job function. We learned that policies are JSON-based, and besides AWS managed policies, there are also user managed policies, which are policies that we create using JSON statements. We also learned that individual AWS services also need permissions to access different pieces of AWS, and we learned how to create roles for those services to assume in order to be able to do the things that they need. As an example, we created a role for EC2 instances to assume, so that EC2 instances can call the AWS API on behalf of other services. For AWS Lambda, we learned that Lambda is managed compute, meaning we can deploy compute functions to Lambda, but we don't have to manage any of the underlying instances or operating systems. We learned how to create a function, and that when we create a function, we can use AWS provided solutions or blueprints, or author one from scratch. We learned that Lambda offers a few different runtimes, including several versions of Python, Node, and .NET Core, as well as Go and Java. We learned that, like many other AWS services, Lambda requires permissions in the form of roles in order to interact with other AWS services. For functions that have already been created, we learned that if we don't want too many concurrent versions of the function to be working at any one time, we can throttle that function. We also learned about using qualifiers and actions to control versions and aliasing so that we can version control our functions. We learned that if we want to test Lambda functions, we can configure test events with example parameters and then test our functions. We also learned that using Lambda's visual editor, we can add triggers, also known as event sources, to our Lambda, which are sources that, when triggered, invoke the Lambda function. We learned that using the function code section in Lambda, we can edit the code inline if we want, or we can deploy a Lambda package via zip file or as a file from S3. We also learned that in the function code editor, we can change the runtime or change the handler. We learned that Lambda has default timeouts that start at 3 seconds and go up to 5 minutes, and that we can also edit the memory that Lambda uses to be between 128 and 3008 megabytes. We also learned that we can pass environment variables to Lambda to use as an input. And then finally, we learned that if Lambda needs to access any resources that are in a VPC, we can deploy Lambda to the same VPC, as well as choose subnets and security groups. For different database options that AWS provides, we learned about Amazon Aurora, which is a MySQL and Postgres compatible relational database built for the cloud that's up to 5 times faster than standard MySQL databases and 3 times faster than standard Postgres databases. We learned how to create a database instance and the different engine options, including Aurora, that are available to RDS database instances. We also learned that for each of the several engine options, you can choose different editions. We learned the difference between provisioned with Aurora, and serverless capacity types, as well as how to choose the right database instance class for us. We also learned about read replicas and multi-availability zone deployment. We also learned how to deploy database instances into different VPCs and subnets, and that similar to Lambda functions, EC2 instances, and several other AWS resources, we can deploy RDS instances into different availability zones or security groups. We learned that if we want to, we can manage our database user credentials through AWS IAM users and roles, and also how to enable encryption for our data. We learned what failover is and how RDS promotes replicas based on priority, and we also learned how to set our backup retention. We also learned about Amazon Redshift, which is fast and scalable petabyte-scale data warehousing, and Elasticache. Elasticache is managed Redis or Memcached compatible in-memory data store that offers blazing fast reads. For AWS Key Management Service, or KMS, we learned that KMS is a managed service that makes it easy for you to create and control the encryption keys used to encrypt your data. We learned how to create encryption keys, as well as decide if the key is going to be KMS or external and imported. We also learned that just like most resources in AWS, we can provide metadata in the form of tags. We learned that who can administer this key, in other words, who can use and configure this key, as well as who can use this key to encrypt and decrypt data in other applications and AWS services. We also learned that key policies are JSON documents just like IAM policies. And as an example, we showed how to encrypt an S3 bucket using a KMS key. For Amazon Simple Workflow Service, or SWF, we learned that SWF makes it easy to build applications that coordinate work across distributed components. We learned that a task represents a logical unit of work that is performed by a component of your application, and that coordinating tasks across the application involves managing inter-task dependencies, scheduling, and concurrency in accordance with the logical flow of the application. We learned to use distributed asynchronous applications known as workflows, which coordinate and manage the execution of activities and that can be run asynchronously across multiple computing devices and can feature both sequential and parallel processing. We learned that we interact with activity workers and deciders by providing them with work assignments known as tasks. As an example, we launched a sample workflow that takes an image from an S3 bucket and generates either a sepia or a grayscale image from it, and then re-uploads it to a bucket. We learned that Amazon Simple Queue Service offers a secure, durable, and available hosted queue that lets you integrate and decouple distributed software systems and components. We also learned that SQS supports both standard and first-in, first-out queues and the differences between those. We learned that standard queues offer unlimited throughput, at least once delivery, and best effort ordering, while first-in, first-out queues offer high throughput, exactly once processing, and first-in, first-out delivery. We learned that you should use the standard queue when throughput is important, and the first-in, first-out queue when order is important. We also created an example queue, and then went through both sending and accepting messages. When a queue has messages in it, we learned how to view and poll for messages. We also learned how to use the Amazon CLI in an EC2 instance to accept messages and how to delete messages from the AWS Management Console. For Amazon SNS, or Simple Notification Service, we learned that SNS is a web service that coordinates and manages the delivery or sending of messages to subscribing endpoints or clients. We learned that in SNS there are two types of clients, publishers and subscribers, also referred to as producers and consumers. Publishers communicate asynchronously with subscribers by producing and sending a message to a topic, which is a logical access point and communication channel. Subscribers, which can be web servers, email addresses, Amazon SQS queues, or Lambda functions, consume or receive the message or notification over one of the supported protocols. As an example, we created an example topic, and then we created a subscription to that topic with the protocol of email and the endpoint of my email address. We learned that once you have a subscriber to a topic, then you're able to publish to that topic, and let that go to any subscriber. And there's that test message. And finally, we learned that when using SNS, you as the owner create a topic and control access to it by defining policies that determine which publishers and subscribers can communicate with the topic. A publisher sends messages to topics that they have created or to topics they have permission to publish to. Instead of including a specific destination address in each message, a publisher sends a message to the topic. SNS matches the topic to a list of subscribers who have subscribed to that topic and delivers the message to each of those subscribers. For API Gateway, we learned that it's an AWS service that enables developers to create, publish, maintain, monitor, and secure APIs at any scale. We learned that we can create APIs that access AWS or other web services, as well as data stored in the AWS cloud. We learned that API Gateway can be considered a backplane in the cloud to connect AWS services and other public or private websites, and that it provides consistent RESTful application programming interfaces, or APIs, for mobile and web applications to access AWS services. In a diagram, we saw how internet traffic can trigger the API Gateway to send traffic either to external apps through APIs or to other AWS services. For Code Pipeline, we learned that Code Pipeline is a continuous delivery service that we can use to model, visualize, and automate the steps required to release our software. We learned that we can quickly model and configure the different stages of a software release process, and that Code Pipeline automates the steps required to release our software changes continuously. We learned that Code Commit is a version control service hosted by AWS that we can use to privately store and manage our assets. We learned that it's a secure and highly scalable managed source control service that hosts private Git repositories, and that Code Commit eliminates the need for us to manage our own source control systems or worry about scaling our infrastructure. We learned that Code Deploy is a deployment service that automates application deployments to EC2 instances, on-premise instances, or serverless Lambda functions. We learned that we can deploy a wide variety of application content such as code, serverless AWS Lambda functions, web and configuration files, and plenty of other examples. And that using Code Deploy, we can deploy application content that runs on a server and is stored in Amazon S3 buckets, GitHub repositories, or Bitbucket repositories. For CodeStar, we learned that it's a cloud-based service for creating, managing, and working with software development projects in AWS. We learned that we can quickly develop, build, and deploy applications on AWS with an AWS CodeStar project, and that a CodeStar project creates and integrates AWS services for our project development toolchain. We also learned about blue-green deployment as a DevOps tool and how beneficial it can be for us. For Amazon Elastic Container Service, or ECS, we learned that it's a highly scalable, fast container management service that makes it easy to run, stop, and manage Docker containers on a cluster. We learned that we can host our cluster on a serverless infrastructure that's managed by Amazon ECS by launching our services or tasks using their new Fargate launch type. We also learned that if we need more control, we can host our tasks on a cluster of EC2 instances that we manage by using the EC2 launch type. We learned that we can create clusters of 3 different types, including the AWS Fargate type that we just mentioned, as well as a Linux and networking type, and a Windows and networking type. We learned that ECS works by sending scheduled tasks to ECS agents, which are agents that reside on individual EC2 instances. We also learned that ECS agents control the metrics that are sent back to ECS, as well as starting and stopping individual tasks on the EC2 instance, and that ECS works by downloading a Docker image from a container registry such as Amazon ECR or Docker Hub, and using that to build its instances. For Elastic Beanstalk, we learned that we can quickly deploy and manage applications using Beanstalk in the cloud without worrying about the infrastructure that runs those applications. We learned that Elastic Beanstalk reduces management complexity without restricting choice or control, and that all we have to do is upload our application, and Elastic Beanstalk automatically handles the details of capacity provisioning, load balancing, scaling, and application health monitoring, and that Beanstalk uses highly reliable and scalable services that are available in the AWS free tier. We learned that to use Elastic Beanstalk, we create an application, upload an application version in the form of an application source bundle to Elastic Beanstalk, and then provide some information about the application. And then Elastic Beanstalk automatically launches an environment and creates and configures the AWS resources needed to run our code. We learned how to create an Elastic Beanstalk application and then to create an environment inside that application. We were able to see that all we had to do was choose a runtime and even a sample project, and Elastic Beanstalk set up a complete web application for us using load balancing, auto-scaling, and everything else we need for that project. We also learned that if we need to, for any application, we can configure all kinds of options for that application, including the software and runtime it's run on, the type of instance we use, how many instances we want, if we want to auto-scale, if we want to load balance, the security that we can control, and all sorts of other options. We also learned about white papers, which are a comprehensive list of technical AWS resources covering topics such as architecture, security, and economics. We learned that these white papers were authored by the AWS team, independent analysts, or the AWS community. We were also able to see which white papers AWS recommends that we get familiar with in order to take the Certified Developer Associate certification exam. We learned that in particular, AWS recommends that we focus on developer-specific white papers, including several white papers on different aspects of DevOps and deployment, as well as a few on microservices, and of course, the well-architected framework. We also spent a small amount of time going over some of the details of some of these white papers.